Hello and welcome to day one, or I guess day two of e-learning Corona style. So we're just gonna move on with the next section in the chapter. This whole chapter is on the Pythagorean theorem, and so you could probably recall Pythagorean theorem involves a right triangle. Yep, has to be a right triangle. Let me draw that a little bit better. Here we go. One side, one leg, call it A. The other leg, call it B. And the longest side, called the, hypotenuse, right. And you have this relationship. A squared plus B squared equals C squared, right? And so this whole chapter, we've been finding values of unknown sides of triangles. Well, we haven't taken it into space yet, meaning we haven't taken it into a three-dimensional place. And that's what, hey, no, sorry, get away from there. That was my cat. And that's what we're doing today. So 9.8, we're using the Pythagorean theorem, but we're using it in space, meaning 3 dimensions. So there's 2 shapes that we're really going to be focusing on. And one of them is called a rectangular solid. Some features of a rectangular solid. It's just a 3-dimensional figure that has rectangles as its side. The important part is they are rectangles, meaning there's right angles there. And so if I was to start drawing a rectangular solid, I could start with this front face. It's a rectangle, meaning there's all right angles here. Now that's important because I could use the Pythagorean theorem to find a bunch of values that might be missing. And if I finish drawing this rectangular solid, think of a pair of dice. Those are cubes. A rectangular solid doesn't have squares for its sides. It can, but it's only rectangles. I think you know what I'm saying. Think of any box, any room that you're sitting in. They're all rectangular solids. Now this is a rectangle, this is a rectangle, meaning there's all right angles here. And if I gave it some dimension by drawing these dashed lines here, now you can kind of see through this box, so to speak, right? You can see the edge on the other side. So all of these are rectangles, including the bottom here. This is a rectangle. It's the same size as the top. The sides here are the same, they're congruent, and the front and back are congruent. That's one of the important features of a rectangular solid. We're also going to be talking about a square pyramid. Those are the 2 3-dimensional shapes that we're going to be doing problems on. So first, let's get into the rectangular solid. I've drawn one here. This is probably a better picture for you to see. So it has some features. It has 6 faces, and each face is a rectangle, and that's important. Why? That's right, because rectangles have right angles, and right angles we can use Pythagorean theorem if we have right angles. All we need to do are draw triangles wherever we want. So, for example, I could draw a triangle here on the face of this rectangular solid. And so, if I know this side and this side, I could easily find C here, right? Pythagorean theorem. So anyways, it has 6 faces, they're all rectangles. It has 12 edges, which the important part about that is that the edges are congruent. So BC here is congruent to FG. FG is congruent to EH. What else? FB. What is FB congruent to? Yep, that's right. You guessed it. EA. It's also congruent to GC. Anyways, there's also 4 diagonals. So a diagonal of a rectangular solid, that's a little different. Do you see this line that passes through the box HB? That's what the diagonal of a rectangular solid is. So you've got diagonals in 2 dimensions. Here's just a regular old rectangle, right? Now this box here is made up of a bunch of rectangles. The diagonal on this one rectangle in 2D This is the diagonal in the rectangle. But when it has 3 dimensions, we're talking about the space inside. And so actually, let me find a box. Yeah, here I have a rectangular solid. The diagonal involves a line that goes from one corner of the box to the other top corner of the box. And this is probably even harder to see it like this, but it's easier to see there. The diagonal goes from the bottom of one corner, it passes through the space inside the box, and then it touches the top of the opposite corner. And so there's 4 diagonals, right? If you took any point here, so from A, for example, and you drew it to the opposite side, it's harder to see in my picture because it's 3 dimensions. If you drew a line from A to G, that would be a diagonal. So anyways, you're usually going to have to find the value, the size of the diagonals in a solid, which means you're going to have to draw a bunch of triangles to figure out your missing values. You're drawing triangles. Why? So you could use the Pythagorean theorem to solve. So anyways, like this problem, for example, the dimensions of a rectangular solid are, so here I'm given a rectangular solid. Now let me draw it on the board here so I can mark up my drawing. So I've got a rectangular solid. Let me draw the face first. E, F, B, A, and let's see, I'll draw the top next. Yeah, don't skip out on drawing these. Practice makes perfect. Plus, it's pretty fun to draw in 3 dimensions. The key is to try and make a bunch of parallel lines. That way it'll look the nicest. That's C. What is this? H. So dashed line indicates that it's behind something. Okay. Yeah. All right. Not bad. All right. This point is D. This point. Got them all. All right. So they gave me dimensions 3, 5, and 7. And here they've marked this side as 3. So BC is 3 here. GC is 5. AB is 7. And they want me to find the dimensions of the diagonal. And so the diagonals are all congruent. There's symmetry going on in this rectangular solid. Think of any box. The line that goes from the corner of the bottom of the box to the top is the same as every line that goes from one corner to the top of another corner, you know? So there's some symmetry here. So all the diagonals are the same. So it doesn't matter where you draw your triangle for this diagonal, as long as one of the sides is a diagonal. So anyways, hopefully you can see this. And you know what? Let me do this in green. That way. Hey man, you really should be able to see it if I do it in green. There we go. So the triangle that I'm focusing on, it's in green. Yeah, it's dashed lines. And maybe if I make it solid, maybe it would be able to see it better. Basically, stick a triangle inside of your box. And there it is. And so look at the diagonal here. The diagonal is HB, and that's what I'm looking for. But to find HB, so the important feature of a rectangular solid is that there are right angles everywhere. Like here, for example, this is a right angle. And so this is a right triangle. I can do Pythagorean theorem. I just need to know these values for if I want to set up the Pythagorean theorem. And so let's see, because there's symmetry going on, if GC here is 5, take a look at GC. The side opposite of GC is HD here. which means that, let me pull that triangle out of there so you can see it. All right, here's that triangle pulled out of there in 2 dimensions. All right, H, D, and B. That's right. So if this side is 5, the side opposite is 5, which means that HD is 5. Okay. Let's see. What else do we know? Well, I don't know what DB is. And so I need to do some more exploration to figure out what DB is, because sure, I have this side. What else do I have? Across from BC is AD. I know that this is 3. Across from AB here is DC in the back. I know that this is 7 in the back here. But it doesn't give me this dimension that I need. I'll call it B. And so what I need to do is I need to see that there's another triangle, namely this triangle right here, the one on the bottom. And this triangle here also has a right angle. Let me draw that on the outside for you so you can see it. Okay. And that triangle is ADB. Okay, cool. Now, I know that this side AD, I already have AD. AD is 3. Okay, get rid of that. I know that AB is 7. And so I can find DB using the Pythagorean theorem. Now, this is sort of like, this is a little detour that I have to take because I need to find this DB to find HB. And so, but I can use the Pythagorean theorem to find this. 3 squared because it's a leg plus 7 squared because it's a leg equals DB here. DB squared, right? And so, you know, you could solve, just moving some stuff around. 3 squared is 9, 7 squared, 49. Okay, so basically DB here, DB equals the square root of 58. Okay, I'm just going to leave that as a improper radical right now. DB equals square root of 58. So I have DB, and I'll write it down here. It's the square root of 58. Cool. Now I can find HB by using the Pythagorean theorem. Again, key feature has to have a right angle. We can't use Pythagorean theorem unless it has a right angle. So now I can find HB. I just need to set up Pythagorean theorem. HB squared. It's on a side by itself because it's the hypotenuse. Equals 5 squared plus the square root of 58 squared. Now the beauty of this is that a radical squared, right? These two cancel each other out. The radical and the squaring cancels out. So all I have is 58 here. Super easy. 5 squared, 25. Cool. HB squared. All right, now I got to solve for HB. Take the square root of both sides. So then HB equals the square root of, let's see, what is this? 7, 8, 83. Square root of 83. So HB equals the square root of 83. I don't know if that could be simplified. I don't think it can. Let's see. 3 and 8 is 11. Yeah. I don't think it can. So anyways, that's how we find the diagonal of HB. Okay, moving on. All right, the next shape that we're dealing with here is a regular square pyramid. Now, remember, we're in the Pythagorean theorem chapter, so we're going to be using Pythagorean theorem. Oh, and let me just recap here. I found HB. HB was the diagonal. I just had to pull this triangle out so I can get a clearer picture of it. And I had to find this missing side, DB, by using this triangle and the Pythagorean theorem. Okay. Next shape. Regular square pyramid. So it's called that because the base of this thing is a square, which means, again, there's right angles here at the bottom, right angles here, And there's also right angles on any lines going straight up, like PR here. That's a right angle there. And so there's a bunch of names associated with these parts. So anyways, a regular square pyramid, again, the base is a square, and there's a lot of features of a square that applies here. And then it has 4 faces that are all, they're all triangles. They're special triangles though. They're all isosceles triangles. So if I draw the face here of my square, these 2 legs are congruent. And all right, let's just pretend that I drew a nice looking square here. So these sides are all congruent. This is 3 dimensions. All right, so let's see. P is called the vertex. PR is called the altitude, because that's the line that drops down from this point here, and it drops down and it hits, let me do this line, this is the line going through the pyramid. It hits the center of the square. Wherever the square's diagonals cross, let me draw this a little bit better for you. Here you go. You see the square, this is the bottom of the pyramid, right? Wherever these diagonals here cross, it's in the center of this square. And so the altitude here drops down from the vertex, and it hits this point that's in the middle. And so what's so important about that? Well, it is perpendicular, meaning there's right angles here. There's a right angle there. Basically, PR is perpendicular to the plane, JOMK. It's perpendicular to that plane that is a square. And so if it's perpendicular to the plane, it's perpendicular to any line that passes through the foot, remember? And so here you can see it. We have a rectangle, or we have a triangle that has a right angle. We could use Pythagorean theorem to solve stuff. Anyways, PR is an altitude. Altitude meaning perpendicular. And PS here is called the slant height. Pretend like you went to Egypt, you walked up to this pyramid, and you decided to walk from the side of the pyramid up to the vertex, the top of the pyramid. Well, the path that you're taking, that would be called the slant height. It's slanted, right? And it's a distance. And so it is also perpendicular. The slant height is perpendicular to KM. Right angle, right angle, right angle at the bottom because it's a square. Those are the most important things. Okay. And so let's see. We can do an example problem here. Let's see. So I have a regular square pyramid. All right. I'm going to try and draw this. I'm going to start by drawing a square. And I'm making it look like a rhombus because I want to give it some dimension, three dimensions, right? And then I'm going to find the middle, and I think I'm going to do the altitude first. That's the line. That's the line that goes from the vertex to the center point on the square. Okay. And here are my faces. All right. So there's my regular square pyramid. Okay. Anyways, it has an altitude PR. Okay, great. PR, that's its name. Slant height PS. Okay, so this is slant height. It's perpendicular. PS. All right. And the name of the bottom, JKMO in the back. All right, we've got all the pieces. Cool. What do we need to find? Let's see. PK is 13. So it's given that PK is 13, right? All right, this side here is 13. Edge. All right, What else is given? I know that the perimeter of the bottom here, perimeter of JKMO equals 40. Now, if this bottom is a square, right, that means that every side here is congruent because it's a square. And so there's 4 sides that make up a square. The perimeter is 40. Divide 40 by 4, and you get 10, right? Which means that every side here is 10. And so if I need to find JK, then I've done that with the given information. They gave me that the perimeter of the bottom here is 40. And so that means that every side is 10, right? 10 plus 10 plus 10 plus 10, that equals 40. And so JK is 10. And what else do I need to find? They asked me to find PS. Okay, I can do that. Well, PS is the slant height, right? And what do I know? Well, let's see. First, you need to be thinking triangles. Look at this triangle here. I'm going to pull that triangle out and represent it in 2 dimensions for you. There you go. So then this is PK. And this was 13, that was given, right? And I need to find PS. Well, to do that, I want to use the Pythagorean theorem, but I need to know one other side, right? If you're using the Pythagorean theorem, you need at least 2 of the unknowns. And so, let's see. I need to know what KS is. Well, what do I know? Let's take it back to the 3 dimensions. I know that KM is 10, right? And so if this is an isosceles triangle, and this slant height here, if it's an altitude, there's a feature of this that it divides this big triangle into 2 congruent triangles, meaning that KS here is congruent to SM. So if these are congruent, and when you add them up, they equal 10, that means that KS is just 5. Okay? Well, now I could use Pythagorean theorem to find PS here. Or, if you remember the Pythagorean triples, you remember a 5, 12, 13? So PS is definitely 12. Why? Because it's a Pythagorean triple. But I'll show you why using the Pythagorean theorem. Okay, let's see. Here's my setup. This is the hypotenuse, KP. All right, so 13 squared equals 5 squared plus PS squared, right? And if I'm solving for PS, let me put it on this side. If I'm solving, I'm just switching sides. I'm going to subtract this. Solving for PS, I'm going to subtract 5 squared from 13 squared. Okay. Then I'm going to take the square root. So PS equals the square root of 169 minus 25, because 5 squared is 25. What does that equal? Let's see. 144? Okay, square root of 144 is 12. So there you have it, PS is 12. So that's the slant height. Oops. The last thing they want us to find is PR. That is the altitude that goes through the middle of the pyramid there. And so let's see. I have PS. PS is 12. Okay. PS is 12. How am I going to find PR? Well, again, I probably need to take this triangle that you see that was formed by PR and RS here, and it's probably easier to just draw it in 2 dimensions off to the side. That way it's not so confusing. Here's PR, and this is what I'm looking for, PR, right? Okay, here, this is PS. Now I know PS, I just found that PS is 12, so I'm going to put that measurement there. RS, do I know what RS is? Take a look at RS. Here's RS. Now if I extend this line and make it pass all the way through, notice this distance here would be the same distance as JK. And since this point is in the middle of this square, these sides here are congruent. This side and that side is congruent, meaning that this is 5 and this is 5, because 5 plus 5 is 10. And so RS is 5. Well, so This one is not a 5, 12, 13 because 13 would be the biggest side. It'd be the hypotenuse. And so for me to find PR, I could use Pythagorean theorem. And let's see. Let me erase this since we already know that. And I'll do my work up top here. Okay, I'm trying to find PR. Most important part is the setup. PR is a leg, so PR squared plus the other leg, which is 5. 5 squared equals the hypotenuse squared, 12 squared. Okay, well let's see, 12 squared is 144. 5 squared is 25. I'm going to subtract it from both sides. Then to solve for PR, take the square root, right? Let's see, 144 minus 25, what is that, 119? Square root of 119? Yeah, I took the square root of both sides. 144 minus 25. Yeah. I don't think that reduces. And so here's our answer. We've got that PR is the square root of 119. That's PR. They asked us to find that value. Now, this might be pretty confusing. The key is to find triangles. And there's right angles everywhere. Everywhere that it looks like a right angle. Meaning that this angle here is not a right angle. It's not a right angle, but this one is. And so these aren't right angles, but if you drew a line on the face, right? If you drew a line on the face, that would be a right angle. Anyways, the key is to find your right angles. Hopefully that makes sense. Anyway, make sure that you ask me if you have any questions. But your homework is going to be page 408 in the book, 408, and let's do problems 1 through 3 and 5. And let's see. Oh, sorry, it's actually page 414. Page 414. Let's do 1 through 3 and 5, and that's it. 1 through 3 and 5. And tomorrow we'll do some more. We'll do page, again, starting on 414. We're going to do problems 7 through 12 tomorrow, okay? So this is going to be on Thursday. This will be on today, on Wednesday.